direct Chablis. Clear direct Chablis.
Gave you too much, now I'm swallowed.
Discretion, maintain level 240.
Now I'm the fool while you're breaking rules.
Hello everyone, welcome to Flat Ups Academy. Today we're going to talk about constant pressure charts, but I figured I'll let you in a little bit of a trip I've got. That's the real Eiffel Tower. It's not a green screen. Lies not across the Atlantic. The dispatchers were kind enough to give us a constant pressure chart of the Atlantic. And I'm going to describe that a little bit, talk to you how it was very helpful to us. Now, on a bit of a side note, one of the cool things about working for airlines is your ability to travel. Not only that, but as a dispatcher, you are required to familiarize yourself with the airplanes that you're dispatching. Therefore, the job itself requires you to go in the cockpit and travel with the pilots to their destinations. The bigger the airplane, the bigger the destinations. It can become a really addictive pastime, and before you know it, you'll be a citizen of the world, traveling to all those destinations you always wanted to visit. Okay, let's start talking about constant pressure charts. Here's a couple of examples I've pulled from the National Weather Service of what they look like. These examples are from sea level all the way up to the 30s and 40,000 feet. They may look like a bunch of symbols that don't really mean anything. Now, the closer we look into them and the more we analyze them, we can start seeing that it's going to give us a lot of information, a lot of very good information, and they're always a good indicator of what the weather is going to be like, what the winds are going to be like. So let's dig right into them. Okay, what I'm going to do is grab this last chart we've got here, and you can see there's all sorts of lines and colors, and it's actually for the North Atlantic, and I'm going to draw it out and explain every bit of it. And I hope that as you're looking at it, you can see some familiar things we've talked about, like the low pressure areas, high pressure areas, some wind and so on. But let's draw it out. We're going to start drawing out this constant pressure chart, and we're going to draw ISO bars. ISO for being equal, and bars for barometric pressure. That means that everywhere where that line is, it will have the same pressure. So let's label these lines. The initial one in the center, we're going to put 996, meaning 996 millibars, just under 1 atmosphere. Next one, 997, and then at 01, meaning 1001. You can already tell right there that the circle inside is going to have low pressure. Now, if we go south of this, we're also going to label those. Those isobars at the bottom are creating a high pressure area, starting with a 1280. You can see how much higher the pressure is over there. That will make a high pressure center. So now we have our area of high pressure and low pressure. If you remember from the chart, the low pressure, there's a trough right there. Usually indicates bad weather. Next to that trough, there was a blue line with triangles. That blue line with triangle represents a cold front. Usually indicates thunderstorms, a lot of convection activity. Next to it, there was another growing warm front up, which indicates low visibility. Stable air, so less convective activity, but still poor weather. With this, you can see how both of those lines come out of the low pressure area. So in a low pressure area, we can expect bad weather. And on the opposite side, on the high pressure area, we can expect good weather. And now I'm just going to continue drawing that same graph that I showed you a picture of earlier. And as it continues, there's going to be an area of high pressure there towards the east. and a trough. Now, one of the things you should notice right away when looking at one of these ISO charts or constant pressure charts is that the wind is going to flow parallel to them. You may think it goes from high to low, but in reality, Coriolis effect takes over and makes the wind fly parallel instead of crossing those isobars. I'll explain this Coriolis effect following. Alright, now to explain Coriolis effect, we'll sidetrack a little bit from ISO charts and constant pressure charts. We're going to draw another Earth with its North Pole, South Pole, and remember the Earth rotates clockwise as viewed from the North Pole. Now we're going to pretend that we have a little friend standing in the North Pole. There he is. And there's the ball. And he's going to want to throw that ball to his other friend. That friend being at the equator. One would expect that if the person in the North Pole throws the ball directly to the person at the equator, that it'll simply go in a straight line, just like the wind would flow in a straight line. Still hanging in the balance, not the life I want to live. I want to take it all, standing tall, fear I weighed the person you are. But of course, nothing is this simple, because we have to remember the Earth is rotating clockwise. Therefore, when the ball is thrown, by the time it reaches the equator, it's nowhere close to your buddy. It actually appears to have turned towards the left, according to the person in the North Pole. So the friend in the North Pole would actually have to throw it indirectly in order for the person at the equator to receive it. Let's put some perspective and some numbers to this. The distance between the North Pole and the equator is about 5,400 nautical miles. So if we were to throw that ball at a very high speed, say at 100 knots, how much time would it take to travel to the equator? The answer to that is 54 hours of travel. That means more than 2 days would have to pass before that ball reaches the equator. Putting such a perspective makes it easier for us to understand why wind doesn't just fly from high pressure to low pressure. And the reason for this is known as the Coriolis effect, or Coriolis force. So now let's just draw a rudimentary constant pressure chart where we're going to have a high pressure area and a low pressure area and some isobars in between both of these areas. Logic would make you think that air would want to flow from the high pressure area towards the low pressure area, because that's what they taught you in high school. But because of this Coriolis effect, the wind will actually take a 90-degree turn and fly parallel to those isobars. Whenever you see isobars, the closer they are, the stronger the wind. The more spread apart they are, the lighter the wind. Now I'm going to give you a real-world example of an actual flight that happened not too long ago, trying to go from Seoul in South Korea to Shanghai in China. This would be the route of flight that the aircraft would take, the more direct route between Seoul and Shanghai. But do you notice something extremely peculiar over Shanghai? We have a lot of isobars. They are all low pressure, and they all seem to be circulating around Shanghai. This, in this instance, was a typhoon. Therefore, our flight had to be delayed long enough for that low pressure area to move away from the airport. Now here I can give you a graphical description of what was going on. There were low pressure systems that I've drawn in blue where you can expect bad weather. Over Shanghai there's a typhoon happening, as well as over northern Japan. Now the isobars that are very close together, I've drawn them in yellow. So you can see there, just over Shanghai, north of Japan, and over inland China, there's isobars that are very close together. So not only is there bad weather there, meaning thunderstorms and typhoon, but you will have very high wind speeds. Hopefully you're able to understand what a constant pressure chart is and why wind flows the way it flows in the atmosphere. Remember, visit us at www.flightopsacademy.com to come get your dispatch certificate and begin your new career in aviation.
Gave you too much, now I'm swallowed.